Hello and welcome to another video. Today we have problem 12 from the AIME exam in 2019. So you can go ahead and pause the video if you want to give this problem a try, but I'll go on to the solution now. So to start, we are given these three vertices that are part of a right triangle. So let's go ahead and draw the complex plane. So we're given f of z is the right angle. We'll have f of z be here, and we have this triangle, something like this. Okay? Now, this is when we need to know a fact that if you multiply two complex numbers together, the resulting complex number, the angle or the argument that it has is the sum of the angles of the two previous ones. So to get from z to f of z, we can see that you've just rotated it 90 degrees as if f of z was the origin. So to rotate a complex number 90 degrees, you would just need to multiply it by I. And in this case, we don't know, this may not be a 45-45 triangle, so we're going to multiply it by Ri. That would rotate our complex number 90 degrees, but that would be about the origin over here. However, we are rotating about f of z. So we're going to have to treat f of z as the origin. So we're going to have to rewrite these 2 points, right? So let's rewrite our points. Let this be triangle ABC. We'll say A prime is, again, we're treating f of z as the origin, so we're going to rewrite A. That will just be f of z minus f of z. I'll do the same for C prime, so that should be z minus f of z. And then we'll get the fact that C prime times the complex number Ri is A prime. A prime over C prime equals to Ri. So I'm going to erase this, and let's go ahead and plug in our A prime and C prime. So that'll give us f of z minus f of z, right? This is just A prime, over z minus f of z is Ri. And let's plug in what f of z is because we are given that up here. So what f of z would look like would just be, and we have minus f of z in the numerator. I'm going to skip a step and just change this minus 19 to a minus 20. And on the bottom, we'll have I'm going to keep going, and I'm actually going to factor out a z squared minus 19z. And you can probably see that this over here ends up being a quadratic. We're going to have a z minus 20 there. And on the bottom, if we were to take out a negative z, we're also going to have a z minus 20. So those will cancel. And now, when we have this, I'm going to let z equals to a plus bi, and we do know what b is, given from over here. We can see that b is 11, but I'll go ahead and plug that in right now. So that becomes And so what does this actually mean? What does this over here, this equation, tell us? We can see that we've got some real parts and we've got some imaginary parts here. But when that is all expanded and added together, we have a purely imaginary part, meaning that all the real parts on the left side will end up being equal to 0. So now we don't have to care about these imaginary parts. We can just figure out what the real parts are. And again, we know what b is. It is equal to 11. So, and now this is just a quadratic, so let's use quadratic formula. And I'm going to take out a 2 squared from this under here, we can see both of them have 4. So I'm going to take out a 2 squared, and that will cancel with the 2 in the denominator. So it becomes 9 squared plus 140, which is 221. So what is our question asking us? It's saying there's positive integers m and n such that one value of z is m plus square root of n plus 11i. What's m plus n? Well, in this case, we don't want the minus part, right? But that doesn't really matter. So let's erase that. This is our real part in our complex number, and so m plus n would be 230. So that's our answer. Thank you so much for watching. Please like, share, and subscribe.